All righty, morning everybody. Let's start seeing some cameras turn on. Get started here in a minute. Just some logistical type things before we get started. Topics we're covering are up in that top right corner. We probably won't cover the third one, or the last one, I guess, fourth one on that list, just because we covered it last week. So there's another good exercise on kind of removing return statements. Really good write-up down there. Go over it kind of on your own pace. That one we probably won't cover in class. It's the same sort of exercise as we did last week. Otherwise, we'll jump into things pretty fast. Just a couple reminders. I didn't have office hours this week. I will next week. Just had some scheduling problems. So keep an eye on the course calendar for that, but any of the TA's office hours or the CA's office hours are good for that. If you need help with setup of Scala, please go to a CA's office hours. I haven't dealt with that stuff in like 2 or 3 years. They're just going to be able to handle that a lot faster. Other than that, is there anything we should cover or any questions before we get kind of going on this week's material?
Yeah, I had a quick question. Last week I attended a different recitation on accident, and I'm in your recitation, but I'm not able to go in person February 15th. Does that mean I need to switch recitations?
Not necessarily. If I were placing bets, I'd say we're not going to be in person on the 15th. That's not an official announcement or anything. So, keep an eye on that. Just right now where the vaccines and whatnot are, I don't think we'll be in person by then.
Okay, so I should just stay in your
stay for now. Otherwise, once that rolls around, talk to me. But for now, no need to kind of mess with anything for now, I don't think so.
Okay, thank you.
Yeah, we might have to have you move, but there's plenty of online sections. As long as you attend one of the recitations, that's really the most important thing. So that'll be pretty easy to take care of at the time. We won't need to like re-enroll you or do anything crazy like that, or we shouldn't need to. I don't think. I'll double check those for you, Rob.
All right, thank you.
Cool. Anything else to go over before we jump into things? I'll hang out for a few minutes afterwards. Stay too if you need to talk to me. I know Matthew, you needed to chat with me, so I'll be around afterwards. Otherwise, let's jump into tail recursion. So I'm sure you guys covered this with Sriram already to some extent. I don't know how much you went over, so we'll just kind of cover it again from scratch to some degree. So there's a big problem with this function we see down here, this factorial function. When we try and run it on a language like Scala, we hit this issue with memory. And so to exhibit how this happens, let's just try and evaluate factorial on 3. So fact 3, if we kind of take a look at the definition over here, we start by asking, okay, is n equals 0? No, it's 3, so we do the else case. So now we have n times, it's too big, this size, n times fact n minus 1, which is 2. And I guess I could replace this n with 2 or 3 rather. Okay, this is going to be a type of evaluation that we'll do a lot. For now, we'll call it just kind of an equational. It's called equational reasoning, what I'm doing here to some degree, where we just kind of go through the program and just equate it to other computations. So here, we know that fact 3 evaluates to n times factorial n minus 1, so we put it on the other side of the equal sign, and we keep evaluating it until we get a solution. So here, well, what can we continue to evaluate? We can't evaluate multiplication yet. We need to first figure out what the result of fact 2 is. To do that, we plug in fact 2. So here we have the 3 stays there. Now we need to look at what fact 2 is. Same thing here, it's not equal to 0, so we do n, which is 2 this time, times fact 1. I think you guys probably see where this is going. Fact 1 isn't all the way kind of evaluated out yet. We can't apply the multiplies to it yet. And so we have now n is equal to 1 in this case. So we go to the else case again. We do 3 times 2 times 1 times fact 0. And then now we go look up fact 0. N equals 0 this time. We return 1. So now we have 3 times 2 times 1 times 1. Now we can finally evaluate all these multiplications. So we get, that's 6 times 1 over here. So we just get 6, right? The observation here, though, is that there are a lot of unnecessary calls that happen. So, or not unnecessary calls, but rather there's a lot of information here that we could kind of collapse and reduce our memory use, right? So here we have to keep track of the 3, this 3 here, the multiplies, and then at each step we're adding basically a command and a number, right? And this is like just horribly inefficient. Why is that horribly inefficient? Because at each step, why not reduce this to say 6 right away? Why not reduce this to 6 right away? And then at the end, we just have 6, right? And that's going to cut out all of this memory there. We don't need that. We can just keep track of one number, right? Way more efficient. And it turns out when you have problems that are really big, so say we're calling factorial a few thousand times, or I want to calculate n on really big numbers, say even stuff that's in the tens of thousands to millions, we're going to get a giant call stack. And you can imagine that call stack at some point exceeds the amount of memory we have. Easy to imagine that case. It's not hard. Storing a bunch of integers is different than storing one integer, even if that one integer is super big, right? So basically, we want to try and speed this up. Well, how do we do that? We're going to try and collect all these numbers, say, in a 6, and do that. We'll give that a name here in a second, but that's what we're going to try and do. So, sorry, my advisor's emailing me. It's that time of day. So how do we reduce this memory use? This is something, to do this, we basically convert this function into what's called a tail recursive function, tail recursion. So how the heck do we do tail recursion? Well, tail recursion is done with this nice little trick called, there's a couple different ways to kind of give this a name, but the one I'll give you is, it's called writing the function in an accumulator passing style. I don't know if Shuram went over this name particularly. You probably don't need to know it. That's what it's called, though. So we're basically adding a new argument to the function. Which accumulates or holds a partial result. Okay, and that's exactly what that kind of red term up here is doing. Is it's just collecting the result that we have so far as we're calling fact. Now I've done this kind of explicitly in each of these cases. It's like, okay, well, what happens if we just collect all those values and call it this red term? Now, how do we do this in factorial? Well, here's how. So here's the example. We'll notice that each part of factorial maps onto this new definition of factorial. So here, I'll just make it explicit. This is the tail recursive version. Okay, so now if we look at this factorial TR, we notice chiefly that it has one more argument, ACC, that's our accumulator. So it's in APS or accumulator passing style. We're going to accumulate the result there when we make recursive calls. We still have the same cases. So note that the base case is still n equals 0 for each case, and we have an else case otherwise. So same cases, we're branching in the same way. Instead, though, of returning 1, we return the accumulator at the end. Okay, we'll get into why that is in a second. And then for the recursive case, instead of doing n times factorial n minus 1, we do n times the accumulator value so far. Okay, and then we do n minus 1 in the same position. That's the same. So the idea is that we move the computation that's occurring on the outside of the recursive call here, and we put it on the inside over here. And instead of acting on the result of the recursive value, it acts on the accumulator. So we can think of the accumulator also as the result of the computation. It's like, what am I getting back from factorial? That's another way of looking at it. That's a slightly subtle way of looking at it. You guys will learn more about that when we talk about continuation passing style. That's later down the road, so we won't get into that today. But you know, why am I allowed to just pass ACC here and not 1? How is that different functionally here? Anyone want to make a stab?
Is it because the accumulator will hold the final value of the factorial you're trying to achieve?
Right on. Yeah. And why is that? What lets ACC do that? What change did
Because every time factorial is called like recursively, we're accumulating the value from the previous call.
Right. And we're doing that in the ACC argument. We're doing it right here. Now, how does, I want to draw another kind of similarity between the two functions. We moved something. So the 1 here no longer occurs there. It occurs here. What's going on there? Why did that happen?
So that it starts at 1 when the function is called, and then it can accumulate in the recursive call?
Right on. So it's kind of just the starting value. It equates to this return value. It also happens to be the identity value for multiplication, which is really nice because it doesn't alter a value under multiplication, right? If we were doing something where we were doing addition, that would probably be 0. Just to kind of leave the value alone, right? So part of being able to make these APS conversions and getting these tail recursive forms is having some identity or having some initial value that doesn't alter your computation. That's really important. There's one other thing I wanted to draw to your guys' attention. Okay, so what about this is tail recursive? What is tail recursion? Because this APS thing isn't necessarily just tail recursion. You can have tail recursion in other ways. APS is just kind of a method for getting there. And we say that tail recursion is basically anywhere where your last term in your function, anytime you make a recursive call, there's nothing else that's done when you return that tail recursion's result. So here, all I'm doing is taking factorial of TR, which lets me completely forget about all of this stuff. I don't need to worry about it anymore because it's been passed in. I'll do an example execution. This will get really clear in a second. Versus over here, when we're done with the recursive call of factorial, I need to do a bunch of multiplications, right, to finish this out. So let's just do this on fact 3 and make it really concrete. So here, I'll call this function fact prime, just so we keep it nice and brief. Just know this is the tail recursive version. So fact 3 is equal to, okay, well, it's not 0 again. So we have now fact prime of n minus 1, so that's 2, and n, which is 3, times our ACC, which starts out at 1 up there. And so that's 3 times 1. That's able to reduce right away, right? So we immediately get fact prime of 2 and 3. Okay, so now we plug in fact prime of 2 and 3. N isn't equal to 0, so we get fact prime of 1 and 3 times 2, which is 6. Now we can do fact prime of, okay, so now we do the else case again, because n is equal to 1, not 0. We get 0 and 1 times 6, which is just 6. I'll skip the reduction there. And now we get 0, so we just return ACC. So I don't even need to copy factorial over that time. ACC in this case is just 6, so we get our result. The thing to notice here is that this right here is much less memory use than what's occurring up here, okay? It's a whole lot less, right? We're not keeping track of all these number values, we're reducing them at each step. And that means we have to keep track of a lot less stuff on our call stack. There's another really good visualization at the top of your notebooks today. I'd encourage you to take a look at that. My buddy David made that probably 2 or 3 years ago now. If you need another example, this is essentially what we're doing though. We're just trying to get it so we're always kind of pushing down. We're always moving downward with our computation. We don't ever have to pop back up, so to say. So you guys should have an example on, I believe, a reverse function. I'll give you a few minutes to give that a try. I'll copy the function down now. Hopefully you have the notebooks pulled up, otherwise this will take a second. So we have def reverse. You guys can go and get started on the exercise. What you're gonna try and do is add an accumulator to reverse and make it a tail recursive function. So I'll write down the original version while you guys are working. Otherwise, I'll just give you 3 or 4 minutes to try that out, longer if you need it. So yeah, get to work, I guess. Reconvene in a few minutes and chat amongst yourselves. If you have questions or something like that, feel free to work together. That's fine by me. Small group, so. All righty, how's everybody doing? Go ahead and say something in chat if you think you have a solution, just so I can keep a head count as we're going. Give you all another 2 or 3 minutes to finish up. Alrighty, let's start going over it. So anyone have a good place where we can start out with a solution here? How can we make this a tail recursive function? There's a skeleton of the function I'd like to see before we start returning any results. If anyone wants some low-hanging fruit.
If the string is empty, then we want to return the accumulator.
Okay, so if s dot is empty, so same base case. Then we return the accumulator, ACC, and then else, right? So we're copying the same form of the control flow here. That'll almost always be the case when you're making these conversions. You want to keep the same branching. But now, what about the else case? So what do we throw in there?
I did s dot slice 0 to s dot size -1, and then accumulator plus equals or plus s dot last.
Okay, so back up for a second for me. Say that a little slower
Okay.
so I can write it down.
Okay, so I got s dot slice from 0 to s dot size -1.
Okay.
Comma ACC plus s dot last.
Where dot last is just the s of n-1, so better notation. Is last a keyword in Scala? Does that work?
Yeah.
Okay, cool. What do we forget here?
to call the function.
To actually call the
Yeah.
call the recursive function. It's easy to forget that though, especially when we're working on a whiteboard or a
Yeah.
fake whiteboard at least. So now I have to figure out how to use the scissors the right way, which is not that way. So I'm just going to kick this to another line, make it a little easier on us. So we have reverse, TR, and then these are the arguments to it, right? Close that out, and that should be our tail recursive function. Did anyone do anything else or do anything super different or, anything like that? Or do we all pretty much do it the same way? Or did we all not even get there and wondering how we did that? I assume silence is good, so we'll just keep moving on. Takeaways there is that you don't really need to do it with just numbers. You could do that with any kind of computation that's recursive, so feel free to kind of play around with that. You guys will get really comfortable with this style of programming pretty fast. It's going to be necessary sometimes in order to get your programs to work. So keep this in your kind of tool belt going forward. Otherwise, we'll jump into grammars. We got about 20 minutes. That's right where I want to see us. So did Shriram cover grammars on Tuesday or yesterday? Yesterday, cool. So I'll just give a quick primer. Basically, grammars are one way we can define data types in a language. So these are kind of roll your own data types. This is a really fun part of this functional programming style we're teaching you guys. It's not exclusive to functional programming by any means. You guys probably encountered these as structs and enumerated types in the past, but they're really useful. We really like them. They give names to things that otherwise wouldn't have names. We'll use them to design programming languages here in a few weeks. You guys will get really familiar with writing these. So the grammar that we want you guys to write here, we give you some stuff to start with. There's a bunch of English level descriptions of this grammar, and we're calling it set. And we use this double colons equals, or I think Shriram maybe used an arrow. It doesn't matter a whole lot. I don't know why he used an arrow. Either one works for us, I guess. And we give you something to start. So here we give you cons of a set and a number n. Okay, can you continue to fill out this grammar? So we want you to be able to add things for the empty set, intersection, union, subtraction of sets, two sets, and the complement of a set. So you guys should have that in your notebook. Go ahead and try and fill this out. Just something to note, and when we define grammars, when you do them, we'll probably more than often use English words as opposed to the operators, just to keep things easy for converting this into Scala. So I'll give you like 1 minute to kind of try and do a couple of those. Once you do one or two, they all follow fairly simply. So take a try at that. Get, I say focus on doing like empty and complement in one of the other operators. So just do that, give you a minute or two to kind of try that out. I'll start filling them in here in a second to give you a sort of hint as we go. So go ahead and get started on that. And I'll describe the operators over here. I'll just kind of write them as well. So All righty, I'm going to start writing a couple of them. So the first thing in the grammar that I'm going to want to write is probably empty. And I'll just write it as empty. It doesn't take any arguments, so we just have it on its own like so. If something has arguments and you write something like the cons case above it. So hopefully that's a good hint for moving on. And anytime somebody wants to give me the next one, go ahead and do so. So somebody give me complement, or I guess any of the other operators works too. Any idea how we construct that as a grammar? Use the cons case, that first case, as an example. That should help you out a lot.
Well, the complement's everything in like a universe. It's not in a given set, right?
Sure. So important distinction here is we're not actually trying to define what the complement is operationally. We're not trying to define the function. We're just giving it kind of notation, right? In the form of this grammar. So we're saying how it can interact with other sets, for instance. So I'll give you guys this one. So for the negation, what we'll write is or for complement, we'll write complement. It's called a constructor because it constructs something of type set or something that's in set. So complement of another set, right? And that says basically what this whole thing reads as is set up here are the constructors, or contains things that are constructed from empty cons of a set and a number, right? And then complements of sets as well. So those things that aren't in the set, right? So we're just describing kind of how sets built, but we're not ascribing to it any kind of like computation. So we're not saying how to take the intersect, how to take the complement, what cons is. All we're saying is that this structure that we've written is in the type set, okay? So it's all purely syntactic, is a word you guys will hear a lot. Any ideas on how we do the last three things? So intersect, union, and diff, given what we just did for complement.
Intersect, you'd have to pass two sets.
Right, so similar form. So for intersect, we're going to give it two arguments, one of type set and the other of type set. Right on. And how about the last two?
Union would be the same thing.
Union's the same thing. And subtraction, I guess on there they call it subtraction, but I guess I called it difference. Same difference. And how about for this one? What do we do?
Two sets again.
Two sets again, right on. Cool. And that's our grammar for set, okay? Later on, we'll describe how to kind of take a set and do computation with it. So how do we calculate the intersect, the union? How do we evaluate is the term we'll use. These grammars, I think Shriram will get into that next week. We'll spend a lot of time talking about how to evaluate stuff. But importantly here, we don't just give these grammars like this in this form to Scala. We have to convert them into what we call these sealed traits and these case classes. So this is going to be your next exercise, and basically we need to just convert this into Scala's language, the language that Scala is going to like a little bit better. So I'll give you the first couple cases and I'll have you guys do the rest. So in Scala, we start out always by kind of declaring the type that we're defining. So we write sealed trait set. That declares the type, says, hey, this is a type. It's the special kind of type called a sealed trait. Don't worry too much about that. And then we're going to write something like case. If something doesn't take any arguments, we call it an object. Empty. And so this corresponds to the empty set. And we say it extends set. Okay. So that's the case if the thing has no arguments. If it does have arguments, we write case class. So it's allowed to take arguments. We'll call it cons. And cons takes something S of type set. We always have to give a name to it for some technical reasons. Don't worry about why yet. And N, which is an int. Close the parens and then say again, extends set. Okay. You guys try and write the last few. So for complement, intersection, union, subtraction, it should mimic a lot of what we saw above. You're just putting Scala syntax to it. So try that out. I'll give you like 2 minutes because we got to do one other thing before we call it for the day. So. Alrighty. What should I fill in these cases with? Ideas. Let's hear it. Okay, Kristen posted a bunch of stuff and it looks good to me. So I'll just start writing these out. So we have case class, complement, and we'll see complement take a single S of type set, and it extends set. Then we have another case class, union. I might be going out of order here. It takes a set S1, or whatever you want to name it. You could name it X and Y as well. S1 of type set, S2 of type set. And then we'll see the same for our last two. So class intersection, S1 type set, and S2 of type set, close that out, and class subtraction, takes an S1 of set and an S2 of type set. Okay, and that's our grammar. So that whole big nasty thing basically just means what's up here. Two ways of writing the same thing. When we write these out by hand, we almost always write them like this. It's just easier to read. Takes up a lot less space. In Scala, we have to write it this way because Scala, there's technical reasons why you have to write it out a little bit more explicitly. What is this good for, though? Why did we just spend time on this at all? Good question, hypothetical student. So the reason we do this is because now we can start talking about these things of type set. We can start writing computations about them. But first we have to figure out how to actually construct things of type set. So for instance, how do I write something like the empty set in Scala using this notation? So this is the notation we're used to, this empty set, or maybe you write it like this. How do we write that in Scala?
Is it nil?
Say it again.
I know this is applying to like lists, but you could use nil or null.
So it's not going to be nil, so don't relate it to lists, but rather the grammar we just wrote. So define it in
Empty object.
So it wouldn't be object, but well, it would be the object, but what's its name?
Did you just
Just
say
empty.
new?
Empty, right. So that's how we're going to write that. So we're trying to define these things in terms of the stuff I'm highlighting in green now. So right on, that's just going to be empty. You don't have to put parentheses after empty. Fun fact for you, that's what object lets you do. It lets you leave off the parentheses. For the rest, you'll need parentheses afterwards, like you're calling a function, except you're not calling a function because it won't evaluate to anything. So let's try the next one. So 2, I want to construct the set that contains the numbers 1 and 2. And the order doesn't really matter for this example, not yet at least. How do I construct that?
Would it be just cons 1, 2?
So cons 1, 2. Is that right? Everyone like that? Almost there. It's not quite there. So let's talk about why. Let's look at the form of cons. So cons up here takes a set and it takes an int, right? What did you just give it? You just gave it a 1 and a 2, right? That's good for the 2. The 2's in the right position. It's an integer. But 1 isn't a set, is it? 1's an integer. So how do I make 1 a set?
Would 1 and 2 be the set? And then you do like comma, like N or something?
No, not quite. So I'll give this one to you guys.
Yeah, like that.
For now. No, that's still not right because we didn't introduce any way doing curly braces or what N actually is. So I'll give this one to you because we're kind of running out of time. So we're going to use cons kind of over and over again to construct a list. So, or a list of our set. So here we've got cons and then we expect another set. So we're going to have another cons. Cons takes a set first, so we give it empty. And we give it 1. Okay. Then as our number argument to that first cons, we give it a 2. Okay. So we can think of this as the list of 1 and 2, or the set of 1 and 2. Another way we can write this that you'll see at some point, I'm sure in this class, is 1, and we use double colon sometimes for cons, onto the empty set or the empty list or whatever. So that's another way of kind of writing lists. You'll see that more as we go forward. That's just how we're going to write that. So how are we doing on time? Yeah, we still got time. So now we'll simplify things for the last few and we'll just do kind of operations on empty sets. So let's do, how do we write the union of the two empty sets?
Union empty empty.
Yeah, right on. So we do union and give it the arguments empty and empty. Questions on how or why we did that? Cool. What's our next one? So this one's where we get a little bit more complicated. So parentheses get involved. So we have empty, union, empty. And we take that, intersect it on not empty. How do we write that?
We use intersect and then throw in a union as a set. With empty, empty.
1 sec, my pen stopped working on me. There we go. So say that again.
So we would use intersect with union as a set inside with empty, empty as the arguments.
Okay, so intersect with union, empty, empty. So I'll just write number 3 for brevity here. And then we should have a second argument, right? What's that going to be? The intersect takes 2 sets, right?
It'd be complement of empty.
Say it again.
Complement of empty, right?
Right on. Yep. Complement of. Oh man, my pen's running out. Okay, we'll see how to use my finger. I don't actually know if this will work. It won't. That's lovely. Okay, so we're typing now. So pretend this lines up nicely because it's not going to, but wait, what is going on? Maybe my app's not working. Okay, because now it's working fine. So we do complement of empty for this one. Like so. Close that out. The last example is similar. You're just adding a subtraction in there. Same principle though. Questions on how or why we're doing this? Is this all clear to everybody? Any explanation necessary?
So what would like be the use of this stuff? So like I understand it and like it makes sense on like what we're doing here, but like what are we gonna use this for, or like when would we use something like this?
Right on. So good question. I ask that as a leading question every year. So, and thank you for asking it, because it's a good one. What we're going to eventually do with this is we could imagine set as a tiny little programming language. Here we just construct these terms, but we can imagine that when I encounter something like the union, I want to actually calculate what the union of these two sets are. And you could use that as kind of a signal to another program to do that computation. So you can imagine, say, I give a case class for something called add, and add takes two numbers, and you know, add doesn't actually have a function attached to it. It's just kind of it's symbolic. It's just syntactic, right? But that tells us to evaluate that add, and then we go look up maybe what does add mean, and we ask, okay, well, what do we need to do to make add kind of reduce this term? That's what we're going to eventually do with it. We can think of it, all of this is the same as notation in mathematics, right? So if I say something like 5 plus 2, this is a signal to me, the person that knows how to do math, that, okay, well, I have this plus, you know, we could write this as, and you actually will later on, as plus 5 and 2. That signals to me to go look up what is plus, how do I do it, how do I actually perform that computation, and do it on 5 and 2, right? And we know that we can, we know our addition, right? So we know that's 7, but there's another way you can do this where you kind of take off 1 from 5. So you do like, kind of do this by parts, and you end up doing 4 plus 3, and then 3 plus 4, 2 plus 5, 1 plus 6, 0 plus 7. When you see a 0, you're done. That's one way of writing, or the piano arithmetic way of writing addition. This is where that's going. So you guys will see that happen in the next couple of weeks with Shriram. We'll start actually giving these case classes kind of interpretations or evaluations to basically start creating programming languages. This is going to be kind of the basic unit, the part that doesn't do anything cool, but it's the first step into making it do something cool. So thanks for asking that question. It's a good one. And we'll kind of pick up with that next week. So I think we'll pick up with that next week, at least. I haven't looked at what we're covering yet, but it should be that. So any other questions before I let you guys go for the week? Perfect. If you need to talk to me individually, I'll hang out for a few minutes. Otherwise, thanks for a good recitation, guys. Same place, same time next week.
Thank you.
No problem.
Thank you.
See you guys.